the intro. My name is Jiawei. I'm from Purdue University, and today my topic is about TopoGroups, context-preserving visual illustration of multi-scale spatial aggregates. So spatial clustering is a common spatial data mining technique that groups similar data points into classes. So spatial clustering can be performed based on different similarity measurement. For example, the distance between different points and some other associated semantics related to the spatial data. And for our work, we are just focusing on the distance-based measurement. And a special attribute of the spatial clustering is that it can be performed at different scales. And hence, the result on the different scales can vary significantly. For example, here's a set of data points we collected last year during a specific event, the Republican National Convention that is hosted in Cleveland. And this is the geotagged Twitter data. And under this specific level, all the data points are clustered as a single group. And when you switch to a different group, different scale, we can see the clustering result changes significantly. And in this view, in this image, there are some different clusters that are formed around the major cities around the Cleveland in Ohio. And then when you switch to an even deeper level, you can find a more fine-grained clustering result. And then this multi-scale space is pretty interesting because it can help explain a lot of spatial phenomena. Typical analysis questions related to this multi-scale space include, for example, what type of relationship exists among the multi-scale clusters, and also how do the associated semantics vary across scales. Conventional approach really require users to navigate across this multi-scale analysis and switching between different levels and mentally memorize or correlate results at different levels. And this is really painful and inefficient. So let's review some of the previous work. So the first direction focused on the assisted navigation, where this type of approach try to optimize navigation operations such as zooming or panning in order to speed up the process to reach the point of interest. And then the second type of technique try to juxtapose the multi-scale results at different levels, either side by side or based on some specific layout method in order for easier comparison or correlation at different scales. So both of these type of approaches require tedious operation, zooming or panning operations. And then recently, some work focuses on the visual summarization, which aim to summarize the multi-scale results into a single visual display. So there's no need to zooming or panning. One of these approaches called scale mosaic contains a set of concentric rings where each ring represents a specific level. And then they focus on the statistical analysis, such as correlation analysis, where the result at a different level can be represented as numeric values, so that they can use, for example, the mosaic or sort of glyph design or other charts to show the results. But our work focused more on the geographic space, spatial clusters. So let me explain our approach by an example. So as I mentioned, suppose end user, say event planner or a police officer, is looking at a major event that happened in a big city, for example, the Republican National Convention in Cleveland. And he's really interested in looking at the spatial phenomena across different scales. For example, from state level to county level, country level, and down to the city level, street level. And then, as an entry point of his analysis, he mapped all those raw data on the geographic space, and also used some existing tools such as heat map or tech map to look at the local hotspot and also the keywords distribution. And then he has to perform zooming operations to look at the results at different scales, which is frustrating. So then he switched to the TopoGroups. So TopoGroups organize the multi-scale aggregates into a hierarchical representation. As I mentioned, for this data set, for example, we have a huge cluster at this level, and then the next level have some more smaller clusters, and then the more detailed level. Actually, these clusters at different levels are organized into a tree structure. And two important property of this tree structure is first, the higher level aggregates or the parents split into lower level ones. And the second, the aggregates at the same level are destroyed, which means they are not overlapping. And for this property, I have to mention that we are only focusing on a single class classification or clustering. So if one single point can belong to multiple clusters, then this condition doesn't hold. So with this hierarchical representation, TopoGroups utilize the idea of combining the multi-scale aggregates into the same visual display. To achieve this, TopoGroups utilize a boundary-based representation to show the aggregate. The benefit of this boundary-based representation is that the visual budget or the visual space that is needed to show this aggregate is minimized, and the area or the space inside the aggregate or the boundaries can be utilized to show other aggregates. And then TopoGroups combine the results of multi-scales into a single visual display, and with some proper overlapping removal and smoothing, TopoGroups provide an occlusion-free representation of this hierarchical structure. So then the end users might be interested in, for example, which cluster is at higher or lower level, and what are their parent-children relationships. So this information is, in general, a univariate attribute. And typical univariate attributes include, for example, the level of scale in this example, and also, for example, the data volume related to different clusters and the geographic space. So in this case, TopoGroups provide some visual encoding for representing the univariate attributes. So here, intuitively, TopoGroups apply a certain color scheme to render the area inside the cluster in order to show the level of scale information. So for example, here the dark blue represent higher level and the dark orange represent lower levels. And with this image, we can find that a cluster at a lower level appears around the Cleveland region, while there are some clusters are generated at different nearby cities, but they are at relatively higher levels, and they vanish at lower levels, which is probably due to the data sparsity. Furthermore, in TopoGroups, we apply a halo effect on the boundary of the cluster. The benefit of this halo effect is that we want to provide a 3D visual effect such that the lower level clusters stack on top of the higher level clusters, which helps enhance the perception of this hierarchical structure. We have conducted a user evaluation to investigate whether color is important or useful to encode the hierarchy information and what type of color scheme is most effective. And we involve some typical color schemes. And for more details about the procedure of the study and the results, please refer to the paper. Having talked about the univariate attributes, now we want to talk about the visual encoding strategies in TopoGroups to encode the multivariate or categorical attributes. So typical examples include, for example, the topics of different clusters. So what are the training topics for different clusters, and how do these topics vary across different scales? So here's a simple example. We have two topics, topic 1 denoted by red and 2 denoted by blue. And initially, TopoGroups draw or visualize the colored segment along the boundaries of the cluster so that the length of the colored segment is proportional to the volume of the category or the topics. But the potential issue related to this design is that so when the users zoom in and only look at a partial view, then this visualization can provide misleading information. For example, in the right view, the users might perceive a blue cluster on the top, but actually, if you refer to the original image, that cluster contains both red and blue. And so to this end, we refine the design by introducing the repeating patterns. So this repeating pattern is achieved by decomposing the large segment in the previous design into a set of smaller segments and tile them along the boundaries. So these repeating patterns can avoid misleading provide misleading information that is introduced by the partial viewing. And the other benefit of this repeating pattern is because the length of the segment is reduced, it becomes easier for the users to compare the length of different segments. We have also proposed a set of design alternatives for different multi-variant or categorical attribute encoding. And for more details, please refer to the paper. And so here's an example of applying the multi-variant categorical attribute encoding in this RNC-based dataset. So by using the topic modeling, we extract 3 major topics, which is RNC-related, drinking-related, and traffic-related. And we use the color segment and draw them on the boundaries of the cluster. And we can find that from an overview perspective, most of the tweets are related to the RNC because they are all red. But actually, most of the tweets are coming from a small region, Cleveland. And the nearby cities have more tweets related to drinking and traffic. And when you zoom in to a detailed level around the Cleveland, we can find similar patterns here. And this probably indicates that a lot of people who either attend an event or attend a protest stay in the nearby cities, and then when they drive to attend the event, they cause some traffic issues. And also drinking-related topics are usually trending in social media. All right, so now let's talk about some limitations of this approach. So first, TopoGroups primarily utilize boundary-based representation and use polygon distortion to avoid overlap. We note that this boundary-based representation just approximates the geographic distribution because it only shows the extent of this cluster, not the detailed information such as the densities or other information. And furthermore, this polygon distortion can produce an inaccurate interpretation of the cluster shapes because it is distorted. And also the multivariate boundary-based encoding only provide an overall summary of the aggregate, and it doesn't really reflect the absolute quantity of different categories. For example, in this image, you can find that compared to the top aggregate, it seems that the bottom aggregate has a longer, red segment, but it doesn't mean that the bottom one has more data points related to the red, because because there exists the inconsistency between the data dimension and the geographic dimension. So a smaller aggregate in a geographic space doesn't really correspond to a smaller data set. In contrast, it can maybe represent a large data set. And finally, in terms of the scalability issue, because we render multiple levels on this map, so increasing the number of levels visible on the map can potentially increase the occlusion on the map and make it hard for the users to look at underlying map elements, such as buildings, rivers, etc. And so our current solution is to restrict the level visible to ±2 levels based on the current scale. So that's 5 in total. And also for the multivariate, multi-categorical encoding, increasing the number of categories can also generate some visual clutter and cognitive overload. So to solve those type of issues require further research and evaluations. So for future work, we want to extend TopoGroups to support more effective semantic exploration across scales. This can be achieved by either by rendering the semantic features such as keywords or topics, either along the boundaries of the clusters or fitting the text inside the area of the clusters. And to wrap up, TopoGroups provides a visual summarization method that aims to couple the multi-scale aggregates into a single visual display for context preservation. And in this work, we explore the design space of different low-level visual encodings for the hierarchical and categorical dimensions. And with this, I want to thank our funding resource, and thank you for your attention. I'm ready to take questions.
Actually, I have a question.
Sure.
The thing is, you're assuming that all the data structure, of course, is a hierarchical.
Yeah.
It does not seem to allow any overlapping groups. Which I think, for example, like there's an example, like there's traffic and drinking.
Yeah.
When it's like one is the subset of the other, that's fine. But what happens if the two things are like kind of overlapping?
Yeah, that's a great question. So I think the question you are talking about is more related to a clustering process of based on topics or other semantics. So for example, if you have a set of data points and you perform the clustering based on, for example, topics or other dimensions, and then you can definitely find some overlapping structures. But in our work, we first clustering based on just the data points, spatial data points, no other attributes involved in the clustering process. So in this case, when you perform the multi-scale clustering, there is no overlaps. I mean, yeah, there's no intersect of different clusters.
Okay, so let's give a hand to our speaker.
Thank you.